QUIC protocol, which stands for Quick UDP Internet Connections, and it's one of the most important transport protocols behind modern web communication. So, if you're watching YouTube or accessing Google services, QUIC is already being used underneath. To understand QUIC properly, we need to place it in the network stack. So, traditionally, web communication relies on TCP at the transport layer, TLS for security, and HTTP at application layer. But Quick fundamentally changes this structure completely. Formally, Quick is Transport Layer Protocol standardized by EITF in 2021 as RFC 9000. It is designed to replace TCP for many internet use cases, especially for the web traffic. Now, what is the core structure behind it? QUIC runs over UDP, but it does not behave like traditional UDP. Instead, QUIC implements reliability, congestion control, flow control, and security, all within one protocol. So, unlike the traditional stack TCP plus TLS plus HTTP, QUIC merges it all. This design is very important as UDP is lightweight and fast but unreliable, and QUIC uses UDP only as a carrier and built its own mechanisms on top, effectively recreating and improving what TCP does but in a more flexible way. Another defining feature of QUIC is that it supports multiplexed streams natively. Instead of treating all the data as single ordered byte stream like TCP, QUIC allows multiple independent streams within one connection. Now, let's talk about why do we need QUIC at first place. Now, the motivation for QUIC comes directly from the limitations of TCP in modern networks. Today's web is highly parallel, latency sensitive, and encrypted by default. So, TCP was not designed for all these conditions. So, our first problem occurs, that is head of line blocking. TCP provides a single ordered byte stream. This means all data must be delivered in one order, even if some parts arrive earlier. If a packet is lost, subsequent packets, even if received, cannot be delivered to the application until the missing packet is retransmitted. This is called head of line blocking. Now, QUIC solution. QUIC eliminates this at the transport layer by introducing independent streams. So, packet loss in one stream does not block others. Connection establishment latency. TCP requires a three-way handshake to establish a connection. So before any application data is sent, multiple RTTs are consumed. QUIC integrates TLS 1.3 directly into the protocol handshake. This reduces the connection to establishment to 1 RTT for new connections and 0 RTT for resumed connections, which significantly reduces latency. Now comes the lack of evolvability in TCP. TCP is implemented in operating system kernel and is tightly coupled with network infrastructure. As a result, deploying changes or improvements to TCP is slow and difficult. QUIC operates in user space, typically within applications or user level libraries. This allows faster updates, easier experimentation, rapid deployment.
All right, so now that we understand why QUIC exists, let's actually look at how it works. And to make this clear, let's connect it with something you already know, which is TCP and HTTP. So, traditionally, TCP handles reliability, TLS handles security, and HTTP handles actual web data. Everything is layered. QUIC changes this a bit. It combines transport and security into one protocol, and then HTTP version 3 runs on top of it. So instead of multiple separate steps, these things are more integrated. Now, internally, QUIC works using two main concepts, packets and frames. Packets are what get sent over the network, and inside those packets, we have frames, which carry the actual data. If you compare this with TCP, it also sends packets, but it treats everything in continuous stream. QUIC is more structured. Each QUIC packet includes things like connection ID, which has a packet number, and most of it is actually encrypted. Even parts that TCP would normally keep visible. Then inside the packet, we have frames. For example, stream frames carry HTTP version 3 data. Acknowledgement frames handle acknowledgement. Crypto frames handle the TLS handshake. So instead of TCP and TLS working separately, QUIC handles all of this together. TCP gives you one order stream, but QUIC gives you multiple independent streams inside the single connection. Now, let's move to another part, which is QUIC versus other protocols. If we look at how the web evolved, first HTTP version 1.1 over TCP, then HTTP version 2 over TCP with TLS, and now HTTP version 3 over QUIC. So QUIC is not just a small improvement, it actually changes the transport layer itself. Now, in TCP based HTTP, before you even send data, you need multiple handshakes. TCP sets up connection, TLS sets up secure, and that adds a little bit of delay. Also, because TCP uses a single stream, if one packet is lost, everything waits. That's head of line blocking problem. Even HTTP version 2, which introduced multiplexing, still suffers from this because underneath it's still TCP. QUIC fixes both issues. First, it reduces connection setup to one round trip and sometimes even zero round trips if you reconnect. And second, because of independent streams, if one packet is lost, only that stream is affected. Everything else keeps going on. One more important improvement, TCP connectionless depend on IP addresses. So if your network changes, say Wi-Fi to mobile data, the connection breaks. But QUIC uses a connection ID, so the connection can continue even if your IP changes, which is very useful for mobile users. So overall wrap is that QUIC is not just faster, it is designed differently. All right, so now the question is, where do we actually see QUIC in real life? So it is everywhere. Google was the first one to develop QUIC. So services like Google Search and YouTube are heavily using it. So whenever you are streaming a video, QUIC is likely being used in the background. Also, HTTP version 3 is the latest version of HTTP, which runs entirely on QUIC. Companies like Cloudflare and modern browsers like Google Chrome also support QUIC by default. So even though you don't see it directly, QUIC is already a part of everyday internet usage. About the security in QUIC, because this is where it's quite different from TCP. First, QUIC has security built in by default as it always uses TLS 1.3. So all communication is encrypted from the start, and there is no unencrypted version like in older protocols. Now, instead of memorizing attacks, just think in terms of what could go wrong and how QUIC handles it. First, let's talk about amplification attack. An attacker sends a small request but tries to make the server sends a huge response to victim. QUIC prevents this by verifying the client first, using address validation before sending large amounts of data. Then there are downgrade attacks, where an attacker tries to force a weaker protocol version. QUIC protects this by making version negotiation secure so it cannot be easily manipulated. Another concern is tracking using connection IDs. QUIC solves this by rotating connection IDs, making it harder to track users over time. And for large scale attacks like DDoS, QUIC uses things like retry packets to verify clients early and filter out fake requests. Protocol is secure, so it needs to be formally verified. Researchers have used tools like ProVerif and VerifPal, which are used to mathematically analyze security protocols, almost like proving a theorem. These tools check whether properties like confidentiality, authentication, and resistance to attacks actually hold under different scenarios. Interestingly, researchers did not find a small design issue in earlier versions and suggested improvements for QUIC security, which is actually a good sign because it shows that the protocol is being rigorously tested and improved. So, overall, quick security is not just theoretical, it is mathematically proved also. Now, let's talk about scalability. And the answer is the design is very scalable. In TCP, if your IP address changes, like switching from Wi Fi to mobile data, the connection breaks. But QUIC uses a connection. Another advantage is flexibility. Since QUIC runs in user space over UDP, it can be updated more easily and avoids limitations of traditional network infrastructure. This also helps with load balancing, where large systems can distribute traffic efficiently across servers using the connection ID. Network analysis. Here, first I'm going to select on an initial handshake of QUIC. I have already filtered it out. If I click on it, we can see that it uses a long header format, which is used during the connection setup phase, because more information needs to be exchanged, like connection parameters and cryptographic data. It uses the crypto packet here, and it also have fields like connection IDs, packet number, and crypto frames, obviously, that carry TLS 1.3 handshake. Now let's move to another packet, a payload packet. We'll see. Now the header is changed to a short header because the connection is established already. So less overhead is needed to make the communication more effective. These packets carry the actual application data using stream frames. Now let's see another packet, which is a handshake packet. It has the destination connection ID. Initial packets have source connection IDs, and these have destination connection IDs. All the information is same. बहुत ही बकवास वीडियो रिकॉर्ड किया मैंने attach my Wireshark screenshots and analysis steps to make it more effective for you guys. Now we are going to summarize QUIC completely. QUIC is a new transport protocol that runs over UDP, and it fixes head of line blocking, slow handshakes, and the inability to update TCP. It works by using streams, connection IDs, and built-in TLS 1.3 function. It powers HTTP version 3 used by Google, YouTube, and Cloudflare today. Security threats still exist, but QUIC has defenses built in. Connection migration makes it great for mobile users, and post quantum upgrades are already being tested successfully, which is the future scope of it. So, that is it for my video. Thanks for watching.